In this talk, I'm going to describe my views on functional programming and declarative programming at a high level. This is going to be not a very technical talk. And here's a brief outline to summarize what I'm going to talk about. First, I will describe why functional programming seems to be interesting, but also weird in a way. And the reason is that functional programming is close to engineering, whereas all other programming paradigms are not close to engineering, they're close to artisanship. And that's why to people who are very much used to programming in the other paradigms, that's why functional programming seems weird to them. I will propose a definition of declarative programming of sorts, which is based on the idea that we need to have a language for problem requirements, and that language should be comprehensible and understandable to people. And yet the same language should be mechanically translated into working code. And so this is why one can say it is specification that is executable. And I would explain how that works and give examples. This is, in my view, the only known silver bullet of programming, declarative programming, understood in this way. Because it is related to a specific problem domain, declarative programming must be domain specific. And we do get a productivity boost for programming within this domain. We need to avoid certain pitfalls, such as the declarative programs getting too long or getting outside of their domain. I'll show examples of that. Then I will argue that functional programming is very much suitable for implementing domain-specific languages. And that may be actually the killer app for functional programming. I will show that it is declarative for working with recursive data structures. And this also means it requires for the programmer to learn some theory of programming languages. So let me begin by saying that when I first started going to meetups about functional programming, I noticed that the functional programming community is different from other programmers' communities, because others are focused on a specific programming language and libraries. And so they talk about how to set up some configs or use the language in a certain way. And the programming people in the functional programming community, they talked in a very different way. They talked with a lot of strange terms, like referential transparency and parametric polymorphism and monad transformers and so on. And actually, this is not an accident. So it wasn't just an accident of the meetups I went to. John DeGoes put up a dictionary of about 100 terms of functional programming. You see there all these existential quantification and F algebra and so on. I went to conferences like Scala, by the way, and those conferences were representative of the functional programming community. And for instance, in 2018, one of the talks at that conference was called the Functor Applicative Monad Talk. In other words, everybody already expects to hear a talk about those things or a talk that mentions those things. So those kind of terms are very unique to the functional programming community. And in my previous career, I was a theoretical physicist. So I recognize this kind of jargon. It is a mathematics-based jargon of engineering. It's very similar to an engineer's jargon. It's based on math, but it is not math. It is adapted to the engineering domain. It is not entirely as rigorous as mathematicians like it to be. Just like in engineering, it is mathematical abstraction that is limited so to speak, on the need-to-know basis. So people talk about proof-functor lenses. They only get as much theory as they need to get the results that they need. This is typical of engineering. So then it got me thinking that this is a very interesting distinction between engineering and artisanship that we are seeing here. That functional programming is actually similar to engineering in how it uses mathematics-based tools. So let's think about functional programming as an engineering activity. What would be an engineering activity? Mechanical, electrical, chemical engineering. They use calculus, complex variables, classical and quantum mechanics, electrodynamics, thermodynamics, all these theories that are mathematics-based. Functional programming uses category theory, type theory, logic proof theory, and lambda calculus. Certainly, functional programming is not those theories alone, but also functional programming uses a small amount of those theories, not entirely the entire corpus of academic literature, just a bit of category theory, just a little bit of proof theory, which is also typical of engineering. Engineers don't use the entire body of knowledge about complex variables, just that knowledge that is necessary, adapted, say, to designing radio equipment and such. Engineers do use a lot of special terminology. I want to show examples of this. So these are, for example, these are materials that engineers use. Stress tensor, these kind of mathematical constructions. Rank 4 tensors, right? Now, if you think about rank n types in functional programming, that's a similar thing. That's a terminology that has mathematics at its origins. I'm not saying that rank 4 tensors have anything else whatsoever to do with rank n types. It's just the terminology that seems to be similar. Look at Lagrangians with non-holonomic constraints. Now, this is something that people use when they do robot design. So they sometimes have some designs that require these non-holonomic constraints. This is a very specialized terminology that is used in engineering. Look at this, Fourier transform of the delta function. Right. This is electrical engineering. This is not some kind of mathematics. This is electrical engineering. You need to learn the Fourier transform of a delta function. Inverse Z transform. Well, again, this is digital signal processing. This is an engineering course which uses this mathematical tool. Look at this, Gibbs free energy. I have two links about this just to show that this is not some kind of arcane thing. Chemical reactor design uses Gibbs free energy and all kinds of other things. Another link for the Gibbs free energy. This is actually a documentation of an engineering company, a Gibbs reactor, that talks about minimizing the Gibbs free energy of the reaction products. So this is really just technical documentation for engineers. There's talking in this language. Now, similarly, programmers talk about free monads. What are free monads? And people answer these questions. Polymorphic lambda functions. And they explain these concepts to each other. Now, the common thing is that this terminology is not obvious, it's not self-explanatory. It doesn't make itself clear without learning about it. So for example, Gibbs free energy is a special term. It means a certain kind of function that satisfies certain equations. It's not just what you would think from ordinary language. It's not, excuse me, it's not energy that Gibbs provides for free. That's not at all what it is. Similarly, free monads. This is a technical term. The word free is used in a technical way. It has nothing to do with the ordinary understanding of free beer or something like this. And all of these things are mathematics-based knowledge. And this knowledge requires learning on its own. It's not obvious. You cannot just come up with it on your own. It's decades of development, and in the case of physics, centuries of development of mathematics and physics. So notice that today programmers do not study those things. They do not study anything of this kind. You go and you study JavaScript or Python, you never hear about polymorphic lambda functions or hylomorphisms, right? Programmers today do not study as engineers do. They do not study courses of the kind that I just showed you, with lots of equations, lots of formulas, and lots of weird terminology. They don't. They study just programming hands-on. And this is how artisans study. This is how artisans learn their trades. It's not bad in the sense that there might be good artisans. And it's not easy to learn artisanship, but it is not engineering. And programmers today do not work as engineers either. They do not use mathematics-based tools to make their designs. Look at what books look like. These are books on mechanical engineering, electrical engineering, and chemical engineering. They're full of diagrams, equations, and formulas, and calculations, and derivations. Look at the books on software design and software architecture. They're all words. Make abstractions consistent and make class interfaces good. That's what they say. They don't explain in equations anything that a programmer would calculate or derive before writing code. In engineering, certain questions have rigorous answers. In functional programming, certain questions have rigorous answers. Questions about design. These answers are not a matter of opinion or experience. They are found via mathematical derivations and reasoning. And the answers to those questions guide the design of, in engineering, of new devices, and in functional programming of new code. Now, it's not to say that the entire design is calculated, or the entire code is derived from mathematics. That is not true, but it is also not true in engineering. Engineering guides the design. It is not automatic that you design a new machine. So here are examples of tasks in functional programming that are questions with rigorous answers. So first example, suppose I want to implement a library with this type signature. So I give a type signature in Haskell and then equivalent type signature in Scala. Now, suppose this is something with your business logic. You have some function that returns this value, and you need to get this value out of it. Can you do it? Can you transform a value of this type into a value of this type in Haskell? It's written quite similarly. Or can you transform back from this type back to this type? And the answer turns out to be that you can transform in this direction, but you cannot transform in this direction. And this is a rigorous answer. It is not a matter of opinion or experience. You can just derive this from certain theoretical considerations. Another example is, suppose I have this data structure. So in Haskell, there's a maybe of a triple, and in Scala, it is called option of a triple. So can you implement the method for a monad for this type? So for Scala, this would be flat map, and for Haskell, there would be bind. Can you implement a method with this type signature that satisfies the laws of the monad? The answer is no, you cannot. It is not obvious, it is not clear, it is not something you already immediately can see. You need to perform certain derivations, calculations, verification, and you find out that you cannot do it. I don't think there is any paper or book that explains the deep reason why this cannot be done for this particular type, but this is something that I stumbled upon, and it seems to be just some kind of accident. But in any case, this is an example of a question that has a rigorous answer. You would want to use maybe this data structure as a monad. So in Haskell, that would be the do notation. In Scala, this would be the for yield notation, but you can't. You can't use this data structure in the for yield notation in Scala or do notation in Haskell, because it is not a monad, and you cannot be made into a monad. So let me now go to the second theme of my talk, which is declarative programming. So declarative has many meanings. People use this word in different ways, and one way they're using it is to say that specifications are programs, or specifications are executable. Now, I would like to make it more rigorous and precise. What I mean by declarative, it is a very specific and much more precise idea than just what a lot of people write. And in particular, being declarative is not a property of a programming language. It is actually a relation between programming languages and application domains. So a language can be declarative for a specific problem domain. And it could be the same language could be not declarative for another problem domain. So when is a language declarative for an application domain? I propose the following definition. First, the domain needs to have a good specification formalism. What does it mean that it is good? Well, it means it is convenient for people. People use this formalism or some specific domain-specific language, as you want, if you want, to talk to each other about problems and solutions in this domain. It must be visually clear notation. It must be convenient to specify problems quickly and clearly, and it must be complete for this domain so that you can specify all problems in that language and talk to each other about it. So first of all, this is a language for people that must already exist. And then there is a syntactic translation from that formalism or language into a programming language, so that the resulting program always correctly implements the specification. And that is what is needed. All these conditions must be met. So there must be already a developed language that people use, and this language should be syntactically translated into code. So that when you look at code, you look essentially at the statement of the problem in the language that you already understand, in the language that you are already using to talk to other people about this domain. I will show examples in this. So to summarize this less formally, a declarative language must be a good and readable DSL for the given domain. So here's one example of the domain is numerical mathematical expressions. And here's an example. So this is a mathematical formula. So the language that people have evolved for this domain is the language of mathematical equations and formulas. Formulas with numbers and functions. So here's a formula. I just wrote some formula, doesn't matter what it is. This is the Fortran code that computes this function. And you see it's a syntactic translation from the language that we all learn when we learn mathematics and to the program. And it is guaranteed that this is correct. This translation is compiled into machine code, and that machine code correctly computes this. Now, Fortran was one of the first languages that introduced this feature, where you just write equations like this, and this even gave the name Fortran. It was a formula translator. So it's a formula that you write that is being translated into machine code automatically. You don't need to write tests for this. You just write this formula. You need to look at this formula, make sure it is correct, and that's it. You don't try to write tests to say, oh, did you actually square this x? Did your code actually square this x? Well, yes, it did, because you wrote it. It is guaranteed that this formula is translated into machine code correctly. This was a huge productivity boost. You didn't have to write very tedious assembly language that computed step by step all these things. Allocated memory, freed memory, and so on, for all these little sub-expressions that you had to write here. You just wrote everything in one line, and it was working. It was a fantastic invention. But this invention is based on the language of mathematics that has been developed over many centuries. And that is why it works. Now, another example is that Fortran is actually declarative for only a certain subdomain of mathematical expressions. Those that are implemented in Fortran are simple one-line expressions, which do not involve any of the more complicated mathematical operations. So for example, there's an equation that involves matrices and summation. Fortran cannot do this in the same way. It does not have keywords for sum over some variable. And so here's the code that you have to write in Fortran in order to implement this computation. This code is not declarative. What does it mean that it's not declarative? Well, do 10, right? So when you write do 10, there's nothing in this formula that corresponds to do 10. 10 is the label of a certain line in code. It has nothing to do with the problem domain. S equals D, or S equals 0. No, not D. Sorry, this is not very clear here. S equals 0. There's nothing in the formula that says that any S must be equal to 0 at any point. So this is something I will talk about also later, but this is a sign that the code is not declarative. You write code such as this, do 10, or S equals 0, do 20, or X of n equals Y of n divided by A and n. Well, this could be part of the formula if the formula were rewritten in a different way. But you write code that is necessary for the program to work, but it does not correspond to anything in your problem domain. It does not correspond to the language that you use to describe your problem. Nowhere in the definition of your problem do you see anything like do 10 or 20 or S equals 0. There's no 0 anywhere. There's no 10 or 20 anywhere. So this is a sign that Fortran is not declarative for more complicated mathematical computations. It is not to say that it is somehow bad. Declarative is a specific property that we're looking for. It is perfectly possible to write code as shown here, but it is more difficult. And it is much more difficult to write correct code in this way. So one of the big productivity boosts that comes from declarative programming is that you already know how to write the problem in terms of the domain-specific language, because you have been using that language to talk about this problem already, and you just translate that syntactically into code, and it's working right away. There's no debugging. So you could forget part of the formula, yes, and that would be to implement the wrong specification. You could do that. You could forget, for example, here instead of 2, you could write 3 by mistake. But that's a much more high-level mistake to make. It's a mistake in specification. It's like saying here is 3 instead of 2. Well, it would be visible much easier, and you could catch that. You could catch that mistake much easier than, say, a mistake where you have do 10 instead of do 20 somewhere. You have no idea what that is. So how to check that? You have to think in a very different way, and it's much more difficult. So that is why declarative programming is really the only silver bullet we know that works. Another example is Haskell, and the application domain is recursively defined algebraic data structures such as trees, lists, and trees. The specification language is an inductive definition of recursive functions on those structures. Here's an example. It's an example from an algorithms book. A binary tree is either an external node or an internal node connected to a pair of binary trees. And here's code in Haskell. A binary tree is either an external node or an internal node with a pair of binary trees. So the same code in Scala looks like this. It's a little more verbose, but it's very similar. A binary tree is either an external node or an internal node with 2 trees. So you see how the definition is translated directly into code. And this is a recursive definition. It says that tree is defined in terms of the tree itself, in terms of the same structure. And similarly, this is the recursive definition of the type. The tree is defined in terms of itself. So if the language allows you to define it like this, then it is declarative for data structures that are recursive. And then here's a definition of a function to compute, say, the height, level, and so on. So the height of the tree is the maximum of the levels of the tree's nodes. So the height of a node is 0, and the height of a vertex is maximum of the heights of the tree's nodes. Right, so the level is 1 higher than the level of its parent, the root at level 0. So the root is at level 0, and the level is 1 higher than the level of its parent. So then we just write this definition, translating text into code. And a similar code will be in Scala. Now, often people say that Haskell is a declarative programming language. So one of the things I would like to make clear is that being declarative is not a property of a programming language. It's a relation between a language and an application domain. So for a different application domain, Haskell is not declarative. Here is an example of code that downloads the data from a server. And here, you already see there are a lot of things that are not declarative. For example, map m underscore. Then, well, you might say, well, get podcast episodes that is clear, we're getting something. But then we have things like filter, map M, do, and so on. Now, it's not clear where the downloading is done. And if you wanted to download from a different server, where would you download from a different server? Or you want to download more data or less data from the server. It's not clear where this is done. It's not formulated in a way that is obvious. And what is this map M, for example? So these are signs that the program is no longer declarative. Now, it doesn't mean to say that Haskell is not suitable for writing such programs. It might be suitable. It's just that once you go outside of the application domain where the language is declarative, programming becomes more difficult. That's all it is. It becomes more difficult. It still probably is good for writing programs and so on, but now the programming task has become more difficult. So there are some other examples, which I would call success stories of declarative programming. The first one I already talked about, the numerical math with infix arithmetic. The second example people know is SQL, relational queries. Select name from employees where employee ID is the same as the building ID something. Those queries are written in a way that is very clear, as long as you don't go outside of the domain. And the domain is simple relational queries. Queries that are not nested, not recursive, and certainly don't rely on stored procedures in SQL or anything like that. Once you go into stored procedures, once you make queries nested, recursive, and so on, programs in SQL are no longer declarative. They're hard to understand, hard to write. And this is because when you say, I want to select all the employees who work in this office and who have this manager, something like this. That is a simple query where you just write a SQL statement that looks like the English that I just said. And if you have a nested SQL query, it means first you have one query where you select some employees or whatever. And then you have another query that selects, say, teams or managers or something. And when you talk about this in the ordinary language, you say, I want to select teams of the employees who are like this. You don't say, I select teams who select employees. You don't say, I select from select. This is not English, but this is what you have to write in SQL when you implement nested queries. And so once you start writing that, it is clear that you are no longer writing declarative programs. So you are stepping outside of the domain. Another good example is auto layout. It is a layout of graphical user interfaces that Apple created for iOS and macOS. In auto layout, you just draw the interfaces. And when you resize the window, you see automatically resizing everything. You don't have to write text or formulas or code and then look at the screen. You just look at the screen and you draw what you need. So this is a declarative way of specifying a layout. When you talk to other people about layout, you just draw the layout. You don't talk about coordinates, 512 pixels or something like this. You just draw the layout. That's the language that we use to communicate. And that's what they translated into their development environment. And that is very effective. And also what I just described is functional programming languages that support algebraic data types and recursion. They're good for tree manipulation. And when you implement a programming language, you need parsing, type checking, and evaluation. And those are operations on trees. And that's why, as I just showed you, code becomes very concise when you write it in a recursive way using recursive data structures. Another example of a declarative language is Prolog, and its domain is logic puzzles. I'll show you the next slide, just for amusement. Here's a logic puzzle. All jumping creatures are green. All small jumping creatures are Martians. All green Martians are intelligent. Nugturks is small and green. Pugvdurk is a jumping Martian who is intelligent. So this is a set of logical relations where you're supposed to solve this logic puzzle by reasoning. And here is a Prolog program. Now, if you look at this program, it is a syntactic translation of this text. All jumping creatures are green. You have to write jumping on the right-hand side and green on the left-hand side in Prolog syntax. But other than that, this is just a syntactic translation. All small jumping creatures are Martians. All green Martians are intelligent. Nugturks is small and green. Pugvdurk is a jumping Martian. Question is, who is intelligent? So you print the result, format the output in this way, and halt the program. Now, if you just paste this text into the Prolog and compile using these commands, the program runs and prints the answer. It is the actual answer. And that is the solution of the logic puzzle. So you see that the program is nothing but a syntactic translation from the English. And the logic puzzles are perfect for Prolog. Now, if you wanted to do matrix multiplication with Prolog, it would be far from perfect. You would not understand what's going on here. Now, this is what you would have to write. And it is not declarative. It is not clear where you are. What is this column, J, mult? What are these things? It's not clear where you're computing the matrix product. If I wanted to compute a different kind of product, where would I make changes here? It's completely unclear. So this code is not declarative. And finally, the example that I want to show is a so-called chemical abstract machine. Now, the chemical abstract machine is a programming language which is called, well, CHAM, chemical abstract machine. This is a programming language for concurrency. And the programming language looks like this in the notation of this paper. So it's not very user-friendly in terms of programming in it. But so this is the kind of programs that you would write in this language. And these programs are executed automatically concurrently. So this language has been implemented as a dialect of OCaml, which is called JoCaml. And now here is an implementation of dining philosophers problem in this language. Now the dining philosophers problem is a very well-known problem in concurrency. And this is the entire solution. There are 5 philosophers. These are forks. And then the philosopher eats and then releases the forks. This is the statement of the problem. Each philosopher will eat. It needs 2 forks for eating. When the philosopher is done eating, the philosopher is no longer hungry and will put the forks down. And then the philosopher who is not hungry will think and then becomes hungry. So this is the entire code of the dining philosopher implementation in this chemical abstract machine, which is implemented as a language called JOCAM. And pretty much in any other language, like C# or Java or C++, the implementation of the dining philosophers is much longer, and it's not declarative. There are lots of things that you have to write that are not obvious. That is not just a statement of the problem. Like these things you can argue, okay, well, you have to define some kind of maximum wait time or whatever. But a lot of this code is like is necessary for the programming language to work. Scope, exit, fork, unlock. Well, what is this? It's not part of the problem statement that you have a scope exit. Fork, yes, fork is a part of problem statement, but not scope exit. So in any case, these are the examples where a language was successfully designed to be declarative for a specific domain. The same language will not be declarative for a different domain. But that's how it is. That's the declarative programming in my view. Declarative programming can fail when the declarative language is used outside its domain, or when specifications become too large to remain understandable. People cannot understand too many details at once, too many specification details or equations at once. So in order to remain understandable, the program must be small. Specifications must be made modular in some way so that each module is understandable in isolation. And the example of doing this successfully at large scale is in mathematical sciences. In every domain of mathematical science, physics, chemistry, and even every specific domain of physics, there is a different notation. And this notation is used in isolation. So you can learn that notation separately, and you only work with that notation. So for example, Fourier transforms have a specific notation where you quickly say, what is a Fourier transform of a derivative of a function? And the definition of the Fourier transform is much longer, but you don't write it every time. So you invent a shorter notation, which is a micro language just for Fourier transforms. And so on. So this is done in every area of mathematics, because otherwise there are just too many details and you don't understand what's going on. So the lesson is domain-specific languages and programs must be small, and they must be kept small. Either the modules must be small, or the entire programs must be small, and the languages must also remain small. Otherwise, you cannot remember all the details. And here are the signs when you get outside of the declarative domain. So you write a lot of code that has no clear correspondence in your problem domain. So you have to write that code. Like you define some classes and getters and setters, or I don't know what, and you say, oh, you need to define a handler for a factory for something. Now, once you start writing things like this, that's not your problem domain. This is something that the programming language needs, but not you. So that's not declarative. Another sign that you are not being declarative in your programming is when code appears to say one thing but does another thing when you run it. So classic example from the Windows interface is that you have a start button, but you have to press it to shut down the computer. Among other things, you also press it to start various things, but you also, so this is confusing, and well, you might say, well, this was just a design. They could made a different button. Yes, they could. But this is just a sign that things have no longer the declarative nature. Leaky abstractions is another sign where things are no longer declarative. Here's an example in JavaScript. Here's a function, right? So I declare x to be 0, and then I have a function f that returns x. So what does this function return when we call it? The answer is we don't know what it returns. The first time, certainly it will return 0 when you call it, but another module could write code like this. It calls this function, result is in y, and y is then assigned to ABC. And JavaScript returns x by pointer. So y is actually a pointer to this x of yours. And now your x is modified. And your x is now no longer 0, not even an integer anymore. And so your function, when you call it, after this module has called this function, which you don't know when that happens, at some time that will happen, and this other module will call that function and execute this code, and then your function no longer returns 0. Although your code says that it does, kind of. And this is a sign that your program is not declarative. It says one thing, but it does another thing. Here are some stories where declarative programming was hoped to give you a productivity boost, but did not turn out to be declarative. And one set of failure stories is a lot of programming languages wanted to resemble English to become declarative. So this was the idea early on. COBOL, AppleScript, and a language called ABAP, which is the language of the software company, SAP. Now, see. Selection screen, begin of block 1 with frame title. So all these things, begin of with select from into corresponding fields of table, else select from, and so on. Message, perform. So all these are attempts to make a programming language that looks like English in hopes that this will make it declarative, because English is declarative. You talk in English about what you need to do. And so that was the goal. But actually, programs become long and unreadable because those languages do not allow you to have high levels of abstraction, and that do not allow you to define small DSLs that you could then abstract and modularize. AppleScript, similar. While your program is small, then it's pretty good, right? Tell application system events to click at the mouse location. Fantastic. It's very clear what that does. Set mouse locations item 2 to display height minus mouse locations item 2. Now, this is perfect as long as your programs are small. When this becomes large, it is completely unreadable. You have huge sentences that you can't really understand. Another attempt to make a declarative language was languages like PL1, where everything was built into the language, every feature, network, databases, everything is a built-in feature. So there are a huge number of keywords. That was the idea. You want to put everything into the language so that you just write code. Now, see what happens here. It's so big and so long, you can't really understand what's going on. It's very hard to work with this language. If term flag, then return. If one of them do. So this was their attempt to make a good language that does everything. The result is nobody can use it. There are so many features. The features interact in ways that they don't know in advance. They could not foresee. and then there are bugs, and then you just spend hours and months and years to debug. So eventually all this was abandoned. ABAP, of course, continues to be developed and used after 40 years, but it's so big that nobody outside of the company wants to use it. And the third example of failure is markup languages, XML and HTML. Now, a lot of people say, oh, HTML is declarative. No, it isn't. Right now, XML and HTML are mostly used outside their domain of declarativeness. So I will show exactly what it is. What was a domain of declarativeness for those languages? SGML, if anyone even remembers what that was, XML and HTML. The idea was that you would write web pages or text, plain text, and occasionally you would insert markup. That was the meaning of the term markup. You will occasionally mark it up. So new paragraph, and then you write text, blah, 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 new paragraph. And then there is a hyperlink to a different document. And the syntax of this markup was chosen so that you could not possibly confuse it with your plain text. This is so ugly and verbose, this thing. It is never going to be part of ordinary text. It would be very obvious where in your text those things are marked up. So that was the assumption. You have a lot of plain text, which is easy to type, and then occasionally you would put markup in it. Here's a new paragraph. Here's boldface. Here's a hyperlink to a new document. And that was perfect, very easy to use. There were just a few of these constructs. You need to remember how to make a hyperlink, how to make a new paragraph, how to make boldface, and that's it. Essentially, you're done. You can do your web pages, and people did a lot of that. What was it now in real life? In real life, XML was used as a data representation language. It's used for config files, for the SOAP protocol, where the payload of internet requests. It has only markup. It has data inside the markup. It is no longer of this kind. It's very hard to read and very hard to use. HTML is now used as a layout language for the graphical interfaces for the web. Now look at this. This is the typical HTML that we have now in the browser. It has nothing to do with this idea of plain text with occasional markup. It's all markup, and it's completely unreadable. So this has become the assembly language of the web. Of course, a very inefficient assembly language, a very verbose, very difficult to use assembly language with a lot of bugs. As a layout language is no good at all. Because the point of HTML was just plain text that goes flowing through the page from one paragraph to another. User interfaces don't flow through the page. They don't have paragraphs. So we're using HTML far outside of its domain of declarativeness. And of course, the result is dismal. It's extremely hard to use HTML. So the work of web designers and web programmers has become very hard. They're no longer reaping the benefits of declarative programming. How do you reap those benefits? You create a domain-specific language, which is small, and you just use it in your domain. How do you implement a domain-specific language? Well, there are two ways of doing it: embedded DSL and external DSL. Embedded DSL means you implement a library in your existing programming language, and you write code just using that library in a special syntax, perhaps. And it helps if your language allows you to customize the syntax to have overloaded operators and infix operators and all kinds of syntax goodies, macros and such, then it's pretty good. You can have a library that makes your language very easy to use, safe, and so on. And functional programming works great for that. There are all kinds of tricks and design patterns to make your embedded DSL in functional programming languages. Or you do the external DSL, which means you make a totally new language with a parser, compiler, or interpreter. Again, for that task, functional programming is good. You have all kinds of idioms and design patterns for parsing, for doing a recursion on different trees. You have recursion schemes. You have GADTs, which allow you to do typed representations. You have these things, higher order abstract syntax or parameterized higher order abstract syntax. Those allow you to translate the DSL directly into the host language very efficiently. The code is short to do this or to do this. And when you do it in FP, the functional programming languages are declarative for describing other programming languages, because that is usually some kind of recursive tree structure in which we define recursive functions for evaluating or type checking or parsing. That is perfect with functional programming. And here's some anecdotal evidence that this is really true. Between 2007 and 2016, there were a number of new languages created where the implementer was just one person. The designer and implementer of the language was just one person. Open source is not a team of 1,000 programmers at Google who are working on the libraries and language. No, just one person who did everything. The compilers and interpreters for these languages were written in Haskell. And I can tell you, I have recently implemented one of these languages called DOL, the DOL language. I'm a big fan. This language is a language for programmable configuration. So it's a replacement of all those template languages like Mustache and whatever they use in Python, Jinja, and so on. So all those languages where you just have string manipulation and templates and a bit of code. Instead of that, you have a highly safe, expressive, powerful functional language, which allows you to express configuration in a very flexible way and yet extremely safe. Now, the grammar of this language is defined. There is very good documentation of how to implement this language. There's an entire grammar is here. It's not very big. A lot of comments here, of course. And I implemented this entire language in about 2 months and about 4,000 lines of code in Scala. Type checking, interpretation, and essentially all the tests, standard tests. It was pretty short. I had to learn certainly certain concepts of programming language theory, but essentially, because I used Scala, I just used straightforward algebraic data types, GADTs, and recursive functions. I did not try to optimize the code. This is certainly a very rough implementation in terms of performance, but I did some performance optimizations that were easy to do, and that's it. So in my view, this confirms the idea that functional programming is really good for implementing programming languages, implementing DSLs, small language. Now, DOL is a very small language. It has very few built-in constructions, and it's pretty easy to implement. So let me conclude now. indeed, functional programming is good, but in a weird way. Why? Because it's close to engineering. Programmers are not used to that. For programmers who didn't expect this, suddenly they look at a steep learning curve. Suddenly they have to learn all the engineering that was done. Imagine you are just an amateur radio person who wants to build a radio device and just buys some parts and puts them together. And then suddenly you decide to learn how it all works. And you're looking at like thousands of pages of electrical engineering and math. Suddenly, digital signal processing is full of math. And you didn't expect that. It's weird. You look at all these delta functions and Fourier transforms and Z transforms, and you have no idea what that is. It's really a steep learning curve. But that makes you an engineer if you learn that. It looks like most people don't want to become engineers. That's fine. I'm not saying that this is necessary, but we need to understand why we are observing these things. We're observing a difference between engineering and artisanship. And the fact that you can create an entire programming language alone in a few months, that is the power of engineering. And the difference between artisanship and engineering is just how complicated you can make things that still work. Now, a big productivity boost comes from declarative programming. It means that you can just write down your problem statement syntactically in a programming language, and it will work. It will be guaranteed to work. It's just like those recursive functions on trees. They just work. In Scala, you write some like type class instances, functor, applicative, traversable, and it just works. It's based on math. You don't have to know this math, but you might want to learn it. You might want to learn some of it. And engineers do learn some of the math. Anecdotally, engineers don't like math. They hate math, but they have to learn it a little bit. So that's how it is. And maybe because declarative programming is really a symbiosis between human tradition of communication between people. Which language and which notation do we talk to each other about this problem? Translated into formally mathematics-based programming language. Maybe that's why the best implementation of declarative programming comes from math-based programming languages, like functional programming, logic programming, Prolog. Prolog is a language that is not much used today, but it would be probably easy to implement languages in Prolog, except for lack of typing. Now, there are some languages that develop upon Prolog to add typing to it, like Mercury and Curry and such functional logic languages. Maybe those languages are actually best for implementing new programming languages, but in any case, they must be using functional programming in some way. And I'm just conjecturing, it is my opinion, that implementing DSLs is one of the killer apps of functional programming. It is something that is hard to do if you don't use functional programming, if you just write straight Java or Python. If you just write something in Python, it's very hard to correctly implement a new programming language in a new, well-working DSL. And even a small DSL is a productivity boost as long as it is declarative for the chosen domain. So I argued that DSLs must be small and programs must be kept small. Well, they can be modular. The modules must be small. So I just said that it was not so difficult to implement the DOL language using Scala. Well, if you look at the documentation, these are the mathematical rules for evaluating DOL expressions. and they are translated more or less directly into Haskell code here, more or less line by line. So certainly syntax, but this is a syntax translation. So you look at the rules for evaluating. So this expression is evaluated to T1 if L is true, L evaluates to true, R evaluates to false, and T0 evaluates to T1. So evaluation is recursively defined through evaluation on smaller sub-expressions. You just translate that into this recursively defined function on a specific case in a big union type, and you go on defining code like this. In Scala, this would be a case expression, very similar in spirit to this one, a little different syntax than Haskell. So this is why functional programming is declarative, and functional programming language make it easy to implement DSLs. And actually, functional programming languages themselves are the easiest to implement. Once you get some initial notions of the theory of the programming languages, and you can read this kind of notation, it's not so bad. You just need to learn a little bit. So be an engineer, learn. This concludes my talk.